We are online. We are live. Okay, let's continue our discussion. This will be continue our discussion on the polynomial method. So to the end of last lecture. So last lecture we had proved the combinatorial Nullstellensatz and the Schwarzschild lemma and saw some applications. And in the process of the combinatorial Nullstellensatz, we proved the following easy version of the Nullstellensatz that we just recall. That is, the statement goes like this. So let F be any field. There's no condition on this one. S1, S2, Sn are subsets of the field. And F is a polynomial. It's an n-variate polynomial. The degree of F, the total degree of F, is less than or equal to D. And it so happens that I'm telling you that F, when restricted as a function on this grid, happens to be identically zero. I'm not claiming as a polynomial it's identically zero. As a function, that is, F is a function on the entire space, but when you look at the restriction of F to the grid, F evaluates to zero as a function. So then we want to claim that F can actually be written as summation Gi Hi, where Gi of X is actually Zsi of Xi, and Zs of any univariate variable is exactly X minus S, S and S. It's the polynomial which vanishes. It's a univariate polynomial which vanishes on this side. And degree of Hi is less than or equal to D minus size of S. People, you recall this? I did this in a hurry last time. I'll quickly recall the proof of this. This was based on one particular fact. We'll recall that fact and then. Is the statement clear? This was a statement we had last time. I stated it in a slightly different fashion. If G1, G2, Gn were 0, then F is 0. But that's the same thing as stating F is 0 on the grid. The way it was stated. F is 0 on the grid is the same thing as that statement. And so we used a basic fact. What was the fact that we had used? So once again, we looked at functions on the grid. Functions on grid. So there were two different set of functions we looked. One was this F, what I called F1, which was S1, S2, Sn. These were the set of all functions on the grid. And it's easy to see is F1 is a vector space, is a F vector space. And furthermore, it's a F vector space. It's an F vector space of dimension product of size of S. We saw this. This is clear. And then we had defined polynomials of individual degree with bounded individual degree. Polynomials. Bounded individual degree, particular, define this class F2, which was, let me call it, is the space of polynomials over F, is n-variate, and it was given mod mod S1, mod S2, mod S1, Sn. What is this? This is the set of polynomial. P belongs to P is a set of if P is a polynomial of n on n over n variables, such that the degree of the ith variable of P was strictly less than size of Si. This was F2. We defined these two classes. One thing which we saw, so F2 was also, so this in particular, right? F2 was also an F, it's also an F vector space. Of dimension, what is the dimension of vector space? It's a number of possible monomials. And how many monomials are there? For in each variable, the number of possible values for x power I can range from xi power j, and j can range from 0 to s1, sj, si minus 1. Therefore, the size of si possibilities. Therefore, this was also of dimension product of size of si. So these two are isomorph in some, they are vector spaces, but actually they're isomorphic vector spaces, but I actually want to say they are actually the same object. And we did say that you can certainly view every f2 as a f2 is a polynomial over the entire space, but you can also view it as a polynomial as a function on the grid, which is what f1 is. Now the question is, I want to say when you view f2 as a member of f1, take a function polynomial in f2 and view it as a member of f1, two things don't collapse. That is, all the members of f2 remain distinct even when you view it as members of f1. I want to actually say that. So how does one show that? So I want to actually say what I want to. We want to say that there's a bijection. Of course, there's a bijection between these two spaces because they are vector spaces of the same dimension. But I want to say actually f2 is f1. There's more than stating it's a bijection. I want to say f2 is actually just f1. But you view f2 as a function. F2 is a set of polynomials. It's defined over the entire f to the power n. It's not just defined on any grid. But if you view it as a function, what you get is exactly f1. That's not true because they are just biject. There's a bijection between these two spaces. 2f2 can collapse to the same object. Okay. Any questions on this?
So we want to prove that in the grid, no two polynomials in F2 are the same. Like they don't evaluate to the same things in points in the grid.
Yes. Yes. So so there are multiple ways of doing it. So we certainly have a map. So what do we have a map? We have a map from F1. Sorry, let's look at it as a map from F2 to F1. We have a map. That is, every function in F2 can be viewed as every polynomial in F2 can be viewed as a function in F1. There is this is the functional map. You take a polynomial, view it as a function that gives you. What I want to say is this map is bijective. Once I show this is bijective, that means every f1 is obtained. In particular, no two functions can, because the dimensions are the same, no two things can go to the same thing. So one way to show it is show that this map is injective. That's one way of doing it. Or because the dimensions are the same, you can also show that the map is surjective. Even then it can show by bijection. So surjectivity is going to be easier in this case. So let's actually do surjectivity. Okay. So is this map clear? What I mean by this function? So I'm taking a polynomial and viewing it as a function f here. And I want to say every function has a polynomial of this. Every function in f1 can be described as a polynomial with this degree pair, can be written as such a polynomial. And let's just ask this: why can do so? To show f2 when evaluated, when viewed as a function is, so this is the function mapping. function is f1 sufficient to show sorry, all I want to say is view this as a function where via the mapping, via the natural mapping, func, and the claim is func is biject2. The short proof of it is, since dimension of f1 equals dimension of f2, sufficient to show func is surjective or injective. Either of them will suffice. Let's look at surjective. So I want to show this can be made surjective. Now I need to take any function f in f1 and show that it can be written as a polynomial of such a degree. That's what we need to show. So in particular, suppose we show it just for the delta functions, a function which is 1 at a particular point and 0 elsewhere. If I manage to show it for this, then certainly it is true for every other function, because it's a linear, every other function is a linear combination of these functions. So, and sufficient to show for delta functions on the grid. So in particular, let A bar belong to S1 cross S2 or Sn, and let's look at the delta function delta A bar of x bar. This is equal to 1 if x bar equals A bar and 0 otherwise. Now I claim, let's look at the polynomial P A bar of x, which is product I going from 1 to n, product. Recall the definition of ZS of x. We had defined it as product of x minus s, s in s. Recall, defined it this way. So I'm going to now just write this as z of s si minus ai of xi by z of si minus ai of ai. Suppose I write this, right? I've written this polynomial. I have not pulled it out of somewhere. Let's just stare at this polynomial. Let's stare at this polynomial. But first claim, I want to claim on the degree of xi of p of a. What's the degree of this?
Si minus, like less than 1 less than si.
It's exactly si minus 1. And let's look at what is P A bar at any point B bar. First, let's look at what is P A bar of A bar.
One.
That's 1. And let's look at P A bar of B bar, where B bar is not equal to A bar. So B bar is not equal to A bar. Therefore, there exists a BI which is not equal to AI. So you go to that particular I. In this, the numerator will become 0. So this is 0. So in particular, PA is equal to delta PA bar is equal to delta A bar, has been viewed as a function. So in particular, it is surjective. Okay, so this question is actually extremely simple. What's happening here? I'm just elaborating this a bit too much. But there are people with me so far. So this basic fact. Once we have this basic fact, let's just recall the proof of the easy null inserts. Any questions so far? The reason I'm elaborating this is we'll come back to this particular proof and see that this proof actually will make a method of this proof and use it for the rest of the lecture. But let's finish the proof of the easy null inserts. We did this last time, but I was in a hurry last time. So let's do this a little more carefully. So that's the important part of this proof. So we had that, what are we given? So we've given f such that where two properties of f was given to you. One is the degree of f was less than or equal to d. Other was f when viewed as a function on the grid was 0. This is what we had. So now what I just wanted to do, the proof was we'll just apply the division algorithm, apply the univariate division algorithm. Ideally, I would have less liked to say f is such a polynomial. Okay, so let me start off. F is such a polynomial, therefore f has to be a member of f2. Why aren't I done that way? F has to be the zero. Because of this, can we say f is a zero polynomial? Because I know f as a function has this property, but then therefore f is a function which is mapping the entire grid to 0, and f is a polynomial, but f is also a function that maps it to grid, and hence I say it has to be the 0 polynomial. Is that statement true?
What is the small d here?
Small d could be anything. It could be much, much larger than size. So that's the reason why it's not true. If I knew that the individual degree of f for each variable was less than size s, strictly smaller than size si,
yeah,
then the previous claim holds. We do not have that thing. So what we are going to do is we are going to, from f, we are going to produce another polynomial which has that feature. That's the whole point of the game right now. If f had the feature that the individual degree of every variable was less than si, the individual degree of the ith variable was less than si, then we could appeal to the observation that we saw before and then say that f is identically 0. But f could have very, very large degree. For example, a polynomial which does not satisfy this, for example, just take to be f to be zsi of xi. It's a univariate polynomial. It's of degree si, not smaller than si. It certainly vanishes on the grid. But it's not It's not a polynomial of the form summation gix. It's straight. So what it's not the identically 0 polynomial. It's not the identically 0 polynomial. So we'll apply the univariate division algorithm. So f of x1 to xn, we'll first divide it by zs1 of x1. It will get some h1 of x1 to xn and some remainder r1. At this point, what do we have? At this point, I want to claim this has got degree of h1 has become less than d minus size of s1. And this guy, its individual degree, the degree of x1 of r1 has gone strictly smaller than s1. That's what division does. The quotient will be of The quotient will be of degree smaller than the degree and what is called? This is called the dividend. The quotient will be the degree of the quotient will be smaller than the degree of the original polynomial and the dividend, and the degree of the remainder will be certainly smaller than the degree of the dividend. I don't know if I'm using these words quotient, dividend, remainder correctly. It's ages since I've used these terms. So, and now you apply the same process now on R1. So now I've gotten Z1, X1, H1. Now I'll write it. Now I'll divide by Z2. So Z2, X2. It's being charged. What's happening? Z2, H2, H2 plus R2. R2 of X1, X2, Xn. Now R2 has the same, this one. Now H2 is the degree of H2 will be less than or equal to D minus mod S2. By the way, the degree of this can be said, and the degree of R1, all I will be able to say is less than or equal to D. The total degree might not have collapsed. The individual degree has collapsed. And for R2, once again, you can say the degree of R2, the total degree of R2, I have no control. It possibly is remaining the same. But both the degree in X1 of R2 has fallen, is not, that can't increase in the process. That is S1, size of S1, and the degree in X2 is less than S2. So we'll keep doing this process repeatedly till at the end we are left with summation ZSI, Xi, Hi, I going from 1 to n plus Rn of X1 to Xn. And what we have at this point is degree of R is, the total degree of R is possibly less than or equal to D. I have no control. But for all I, degree of the ith variable of, sorry, this is Rn, of Rn is strictly less than Si. Now Ri is a function of the type, Ri is a polynomial of the type which we talked about before. Its individual degrees are bounded. Now, because we know that F restricted on S1 cross S2 cross Sn is 0, and ZSI certainly when restricted to Si is 0, we also have that Rn when restricted to S1 cross S2 cross Sn is 0. Because in this equation, F is 0 on the grid, this is 0 on the grid, therefore this also has to be 0 on the grid. But now R is a polynomial of the type which we care for, and it is 0 everywhere on the grid, therefore R has to be the identically 0 polynomial. But by observation, R has to then be identically 0. Hence, F is actually equal to ZSI Xi into Hi. It's identically true. This is a polynomial identity. Okay. Are people with me? Any questions on this so far? Okay. So I want to move to the next. There are two problems which I want to talk about, but I want to say this proof of F1 being equal to F2 is actually a very interesting proof that's going on over here. What was F1? F1 was the space of functions on a particular class. F2 was the space of polynomials, some related polynomials. In this particular example, we were able to show that we knew that the dimensions of both these spaces were the same. But I want to say this technique, that is, here we already knew that F1 and F2 had the same dimension. This need not be always the case. So we will show I want to say that this proof technique actually is going to tell us something. Suppose we had A was some arbitrary set. A is some subset of, say, f to the n. Typically, it will be a subset of 0, 1 to the n. A is some arbitrary set. And we look at f, which is a set of all functions from A to f. This is once again a vector space. What's the dimension of this vector space?
Series of A.
Yeah, so this is a vector. F is a F vector space of dimension size of A. Now, suppose I was able to show that F was spanned by, so suppose on the other hand, we were able to show F is spanned by, say, polynomials P1, P2, Pn, polynomials of a particular type. So F, now I'm viewing it as, F was originally functions, but now I'm viewing it as some polynomials. F was contained in this. Was contained in this. What can you say here? Because something is contained in the span of this one, let's call this guy F2. The dimension of F2 has to be smaller than or equal to M. Is that okay?
So I mean, like there's some independence of P1 to P1. We are assuming it, right? Oh no, I mean this is this.
No. I'm not assuming anything.
We don't need that. Yes,
we don't need it. It's smaller than M.
Yeah.
But this will tell you. But this will tell you that size of A is less than or equal to M. This is one. So suppose sometimes you have to prove that a set is not large. This offers you a way of trying to prove a set is not large. We will look at the set of functions on that set and show those functions can be described, can be spanned by certain polynomials. And we can find a spanning set of polynomials which are not too large. And that, if that is not too large, that number puts a bound on the size of the set. This is, of course, a very trivial fact, but we will show that certain very nice polynomial identities you can actually prove just using this observation. So this is just a sort of a meta statement I've been talking about. That is, this approach which we did is actually, you have some set A. A has some properties, and I want to now show how large can A be. You want to understand this? One way of trying to do it is you look at the function class on A, show that all functions in this can be described, can be spanned by polynomials of a very restricted nature. By the way, these don't have to be polynomials, they could be anything. But because we are in the polynomial methods, all our examples will be coming from polynomials. It could be anything. The span of some M functions, if you can show that, then that shows that the size of A can't be more than M. So this is a method, and we are going to show two nice proofs which are just based on this one principle. Okay. Any questions so far? And then I will enter into two examples, and they come two applications of this method. Okay, so let's go on to two applications. So this above is a method to bound the size of a set. By the way, those of you who were taking the complexity course, I wanted to announce it on Monday. If you had attended Ram Prasad's lecture on Monday, he did this theorem due to Rasborough and Spolensky. That basically the heart of it is this method. They want to bound some set size. They actually build this. This is a technique that will be used over and over again. So if you want yet another application for the people who didn't attend the complexity class, a good thing is to go to the Monday's lecture on complexity, and that is an example of a setting where this method is applied. But let's look at an application. Let's look at application to begin with over here. Application 1. This is the, actually, let me not call the Frank, let me just directly write the Frankel-Wilson theorem. So what is the Frankel-Wilson theorem? The Frankel-Wilson theorem is stating that suppose you're given F is a family of sets, family of subsets of n, 1, 2, 3 up to n. That is, F is a subset of 2 to the n. And I've told L is some L1, L2, Ls. Each Li is a non-negative integer. I'm saying that suppose F is L intersecting. What do I mean by that? That is, for all distinct AB in F, if you look at A intersection B, that is something which is strictly smaller than A, strictly smaller than B, because A and B are distinct. No, that need not be true. A could be a subset of B. It is strictly smaller than one of the two. I want to claim this actually belongs to L. The size of this set has to belong to one of these S numbers. That's when I call it L intersecting. So L intersecting is a family of subsets is called L intersecting if every distinct pair in this family of subsets, their intersection is of a member of L. Okay. What is one such? So suppose one example of L is 0, 1, 2, 3 up to S minus 1. So suppose we work with 0, 1, 2, 3, S minus 1. So what I want to say is basically I want to put a bound on the size of F. That is, F cannot be too large. But before that, let's look at an example. So what is an example? Let's look at an example where L is 0, 1, 2, 3 up to S minus 1. What is an example of a family of subsets?
You can take all subsets of size S minus 1.
Just S minus 1, then their intersection will go up to S minus 2 only. Because I'm taking distinct guys. So all subsets.
Oh, yeah, okay, S, yeah.
So for example, so F I could have set it to be equal to, shorthand, I'm just writing it as this object. All subsets of n of size at most S. And what is the cardinality of F in this setting? It is basically summation n choose I going from 0 to S. Okay. So this is a setting. What we will show is this is the largest you can take. Any such thing has to be of size. And because this number is going to come so often, I'm actually going to define, it's going to come twice. Phi S of n is going to be defined to be summation n choose I equals 0 to S. I'm going to define this there. This is just usually, actually, I don't know why this is usually just defined as n choose less than equal to S. Let's just stick with that notation. Or should I build up a notation for this? Is less than or equal to n choose less than or equal to x, which by definition is summation n choose I going from 0 to s. Statement of Frankel-Wilson here. So it's basically this fact. If F is L intersecting, then size of F and L is set size. Any questions on the statement of Frankel-Wilson? So this, we're going to show this by exactly doing the other method. We want to put upper bound on size of f. So we will build a class of, so the way we are going to use the polynomial method is we're going to look at the set of all functions on, we're going to build a function class on f itself and then talk about it. Okay. I should be a little careful. Let's not call this f. Let's call this small f. Because capital F, I've been using it for capital F, I've been using it for the functions on this class. That's what it is.
There's another script F here. Script F is L intersecting.
The script F is L intersecting. Yeah. That's also another. Okay. Questions so far? So let's go to the proof. Let's jump into the proof of this. So let's look at f, which is the set of all functions from f to, I don't care which field, let's say the real spot. Once again, f is an R vector space. F is an R vector space of dimension exactly size of f. Now I want to say that f has some nice, f can be written spanned by a small set of polynomials. And for this, we are going to crucially use a fact. So suppose let's recall the usual dot product vector, this one. So this is just usual dot product. This is summation xi yi, I going from 1 to m. X and y are sitting in Rn. So suppose S and T were subsets of n, and one S and one T are the corresponding indicator vectors. What is 1S dot product 1T?
1 of S intersection T. No, sorry, it's the size of S intersection.
Are everybody with me on this? This is important for this, because this is where the intersection is going to come. So the dot product behaves nicely for if the dot product between two indicator vectors is exactly the size of the intersection. Okay? So this is exactly S intersection T. So an equivalent way of stating that f is L intersecting is stating that for all distinct AB in F, the dot product of 1A and 1B belongs to L. This is just a reformulation of the whole setup. Okay. Now for each, I'm going to build a polynomial now. For each A in F, let's build this polynomial PA of X. PA of X is going to be an M-variate polynomial over the reals. This could have worked over any field, but let's work over the reals. Or x1, x2, xn. Let's first call it PA tilde. I'll then come to what PA is. PA tilde of X, I define it to be the following quantity. The inner product of 1A with X minus Li, where I range over all I such that Li is less than the size of A. Okay, people with me. This is definition okay. Why do I want to do this? Let's stare at this a little bit. This one. So F was a sequence of sets. So let's assume F is of the form A1, A2, A1 in non-decreasing order of the sets. Let's write them in non-decreasing order. Order of size of the sets. Okay. Now let's ask, what is P tilde of AI of AI? Can it be 0?
No, because Li is less than the
So
size of A, right?
that's the first observation I want to make. This is not equal to 0. Okay. Now let's look at I less than j. Let's look at P tilde of AI of 1 AG. What will this be?
0.
It will be what?
If you took it in non-decreasing, or
Non-decreasing.
yeah. So every a every AI. So wait, are you taking this? Okay, you're taking the sets after AI. So the
Sorry,
intersections with
sorry,
A.
sorry. I should have flipped this. I should have flipped this. This was j less than I. Intersection between AI and AJ is a number certainly less than size of AI. So it will appear in this summation. And hence it will zero out.
Did you want to take product?
Oh yeah. Sorry, what did I say? I certainly want to take product. So then this is what? This is 0. So what I want to say is these two observations together, what do you say? These functions PA tilde, which I viewed them as functions, they form a sort of a triangular system. And these imply that the PA tildes are actually linearly independent when viewed as functions. Because it cannot be the case that any one of them can be a linear combination of the others, because take the last guy in the linear combination, which is the guys previously, that guy will be a sum of the rest, and it cannot happen. Let's stare at this. I want to say star implies P tilde AIs when over I is linearly independent. Suppose not, then there exists something of the form, let's write it, let's be a little pedantic about it. Alpha 1 PA1, sorry, PAI1 plus alpha 2 PAI2 plus some alpha R PAIR equals 0. And I'm going to assume I1 is less than I2 is less than IR. That's what, and
alpha is unknown.
alpha vector is not equal to 0. But then let's call this function f. Let's call this function f. Let's just look at f of indicator function of 1AIR. This is certainly just alpha r. This is certainly alpha r. Alpha r into some non-zero way. Because, sorry, this is not what I want to write. What do I want to write? Which one should I put? Should I put the lower guys first? The upper guys first. Second. Sorry, let's not do this. Let's put.
No, so I guess here we can say then P of AIR.
Let's look at f of AI1. Look at f of AI1. F of indicator of 1 of AI1. When I plug this into this, it's going to. When I plug it into this, it will evaluate as 0 because all of these are higher up in the thing. Only this is the only thing which will possibly evaluate to 0. So this will be equal to just alpha 1 into something non-zero. But this will force, because f is 0, this will force alpha 1 to be 0. Now start with the next guy, alpha 2. You will get that alpha 2 is 0. You keep doing it one after another, all of the alphas will be forced to be 0. That will imply, continuing, you will get alpha bar is 0, which is a contradiction. All I claim is the P tilde AIs are linearly independent when viewed as functions. So in particular, they are also linearly independent when viewed as polynomials. If there is a linear dependence as polynomials, there's a linear dependency as functions also. It goes, one direction is clear. Okay. So it's linearly independent. So and in particular, you have a distinct thing for each of the polynomials. Therefore, the dimension of this space, the dimension of the space spanned by the PIAs is exactly the PAI span the class calligraphic F which I'm talking about. They are size of F in number and they are linearly independent. Therefore, they are they form a spanning set. They form a basis for the class of functions we were talking about. Okay, but so PAS are this. PAS are a linearly independent system. But let's go back to the definition of P. Let's go back to the definition of P tilde AI. This is how I defined it. So the P tilde A of X was defined to be product of 1AX minus Li set of all Li less than size of A. This is not necessary. So let's just open this out in the n variables. This is not necessarily a multilinear polynomial. There is its individual degree in each variable could be much larger than what was there before. It's much larger. It need not be 0 or 1. It could be much larger than 0 or 1. So one thing I want to say is PA tilde is not multilinear. But everybody knows what multilinear is. If anybody doesn't know, let me know. Multilinear means just that the individual degree of each variable is less than or equal to 1. They can be, total degree can be large, but the individual degree is all less than or equal to 1. And one way of multilinearizing a polynomial is you just replace every higher power. If a particular monomial has a higher power than 1, just replace it by 1. Of course, if it doesn't have that particular variable, you don't do anything. Multilinearizing is just reducing all the powers, higher powers to 1. So let PA be the multilinearization of P tilde A. People with me?
I mean, here, like, we would only be caring about x, which are characteristic vectors of elements.
Because we only are, because of this, why did I do this? Because this proof of, I want to claim even the PAs are linearly independent, because you only care about this proof only required at the evaluation of at 0, 1 vectors. 0, 1 vector, when you multilinearize it, the value of the function does not change. That's the whole point. Why am I multilinearizing it? Multilinearizing does not affect the value of the function at 0, 1 in vectors. Hence, even the set PAI is linearly independent. So let's write it this way. Even the set PA, A and F are linearly independent, because even PA satisfies this. PAI of 1AJ is 0 if I equals j, and if is non-zero if I equals j, and 0 if j less than I. This is all that I needed for independence, proving independence, and that statement is unaltered by this. Okay, so you have these PAs. Okay, where am I going with all of this? I have given a bunch of PAs which are multilinear, and they also happen to be linearly independent. What is the largest monomial in any PA? How large can a degree be in any PA? Let's stare at this definition again. I'm going to multiply this out. If suppose this product was not there, just this guy, each element, this is just linear in each variable. This is just linear in each variable. And then I'm multiplying it out this way. How many guys am I multiplying? This product is at most of size yes. This is where I'm using the fact that capital L is of size yes. Want to make one observation, that any monomial in PA is of degree at most yes, because of the way I have defined PA. So in particular, PA can be written as a sum of, as a linear combination of xi, where xi is just product of xi and I with, for all I is of size at most equal to s. But how many of them are there? Hence, all I want to say is span of PA, A in F, is contained in span of Xi mod I less than or equal to S. This we saw was exactly equal to the size of F. This is exactly equal to summation n choose I equals 0 to S. This is exactly the principle which we had talked about. That's the end of story. Lo and behold, all of the setup was just to get to this, and that puts a bound on this. It's an amazingly beautiful proof. Just stare at it. I spent more time than necessary for it. I just built it up, but look at the proof. It's a beautiful proof. It just says to put a bound on the set, we review it as a class. We look at the class of functions on that set and show that that class of functions can be when viewed as polynomials as specific properties, and those to show that that polynomials, because of the way it's been defined, actually can be spanned by a small set of monomials or small set of this ones, and hence the original family that we talk can't have too large a cardinality. Any questions? Okay, this is one example. The next example I'll go, we will actually talk about VC dimension. This is going to be a topic for the next lecture, but we will prove something about VC dimension using the same method. So I started off in this lecture itself, and we will see applications of VC dimension in the next lecture. So I'm going to well into new topic called VC dimension, but it will actually be the application. The application 2 will be, so the application 2 of the problem which I'm going to be talking about is going to be towards VC dimension, in particular something called, we'll see, it's going to be what's called the Harsha lemma. I will need some basic background before I even state the lemma. But any questions on the previous thing so far? So once again, it's the same, it's this amazing thing. We want to put a bound on a particular set. We look at the class of function, we look at the function space on this set and show that this function space can be spanned by a small set of functions, and hence that puts a bound on the set. This is one way of showing an upper bound on the set. There's also a way of, it also shows you how to show a lower bound. Build a function class and show a bunch of linearly independent functions in this. That puts a lower bound. These are both these methods. So put upper and lower bounds on class. So several combinatorial inequalities can actually be reproven in this framework. That is, just view them as a function. You want to put a upper bound on a set. You look at the class of functions on that set and show that they can be spanned by a small family of functions. If you want to prove a lower bound on a set, view the same class of functions and show that there are a bunch of linearly independent functions in that class. That will put a lower bound. And this is a very nice techniques to keep in mind when you want to prove upper and lower bounds. Okay, but let's go to VC dimension 1. So I want to talk about, so let U be a universe of points. This could be both finite, infinite, I don't care. U could be just a set of points 1 to n. It could be all points on the real line. It could be all points on the plane. It's some universe of points. It's both finite and infinite, I don't care. And F is a family. Let's call it yes. It's usually called yes. Yes is a family of subsets of U. It's not all the sets, but it is some family of subsets of U. Some subsets of U. So in particular, you're given a set of n points, and you said these sets I care about. Or you're possibly given on the real line and you say these are the subsets I care about. They might have very great structure. I only care about subsets which can be described as intervals. One example is I only care about subsets which can be described as intervals. Suppose you were, so let's look at some examples. Example 1 is U is the real line and S is all those, is the set of all intervals of the form AB. A, B both belong to R and A less than or equal to B. That's one family of this ones. This is one example. A second example is U is the plane. And what is S? S is, so this is the plane. And S is take any, defined by any hyperplane, it is all points on one side of the hyperplane. That is, so S could be sets described by a hyperplane. Okay. So that's the setup we are going to be in. And now let X be any subset of U. It's not necessarily a family of the subsets. It's some subset of U, but X is finite. Okay. And let's look at this class X intersection S as I'm ranging over all S. So just look at the set of all subsets of X that happen when you intersect X with all the family in the subset in your set system. Notice that this certainly is a subset of 2 power x, not the size of x. It's a set of what can you get? You can only get subsets of x. You can't get anything more than that in this process. And what we will say, so this is an important definition, we'll say that X is shattered. Let's make it this one. A finite set, this is only a definition. A finite set X of the universe is shattered by the set system S if this happens to be an equality. That is, you get, when you intersect it with S, you get every possible subset of X you actually achieve. Then you say it is shattered. In every way, you can break it up, you can break up by X into every possible way. That's why you call it shattered. So let's call this X S if X, let's not call it this way. That's right. Yes, X, to define it to be this way. If Sx equals 2 x. Okay. Okay, let's go back to our examples to get a handle of this. So suppose I give you a set of, let's look at the first example. I give you a set of 2 points, 2 distinct points. What is it shattered?
Yeah, you can take some, 2 distinct points, some interval which covers only 1 point and some interval which covers.
So you can give me an interval which covers 1 point, 0 point, 2 points. You can give this one. Therefore, if you give me 2 points, it is shattered by it. Suppose I give you 3 points. Can it be shattered by it? By this set system?
Yeah.
How? Suppose I give you 3 points on a line and I take the 2 extreme points. What is an interval?
Oh, I see. You can't.
Those 2 points are not the interior point.
Yeah, you can't have that.
So 3 points. You can, so there is a set of 3 points which is not shattered by the first set system. And once again, let's look at the second example. Let's look at the second example. Are 2 points shattered by it? They are certainly 2 points. What about 3 points? Are they shattered by it?
Yeah.
Huh?
Yeah.
Once again, not true. If the 3 points are on a straight line, they need not be shattered.
Okay, if they're
on a straight line, they will not be shattered.
Yeah, if they occupy the whole space.
Points which are non-collinear will be shattered in the second example. Are people with me? This is an important example. VC dimension is more than the VC dimension is an important concept. So let's just stay back. I want to say in the second example, 3 points are shattered if they are non-collinear, they are shattered by it. Now let's look at 4 points. Are they shattered? 4 points. Let's just take a corner, the elements of the 4 vertices of a square. Can they be shattered?
The 4 vertices of a square can be shattered, but if you take like a triangle and inside that one point.
The triangle and one inside cannot be shattered, I agree. 4 also cannot be shattered. Take the diagonal, 2 diagonal, which is a convex thing which is going to just pick those 2 and not the other 2. Anything which picks these 2 will also have to pick.
Yeah.
So actually, I want to say there cannot be any size of set of size 4 that is shattered in the second example. Every set of size 4 is not shattered. The maximum set of a size that is shattered by the hyperplane is only 3. Even 3, not all sets are shattered, but the maximum size that is shattered is 3. Are people with me on this? And the first example, the maximum set of a size that can be shattered is 2. 2 is the size, the maximum set of a size that can be shattered. In the second example, 3 is the maximum set. There is no set of size 4 that can be shattered. And why is that? This is follows from Radon's theorem. So, but what I want to know, this is going to lead me to the next definition. So pi m of a set system, let's call it the other way, pi s of m is max over all x subsets of u, size of x. Even though u is infinite, I'm only ranging over finite sets. It's the maximum over, sorry, what I had written previously was fine. It's x subset of u, size of x is equal to m, size of 2 power x. Not 2 power x. What am I writing? What am I writing? The number of sets that is shattered by, which is this. Pi m is this largest set of, is the largest amount by which a set of size m is shattered by. Is not shattered, is broken into. Okay. And the VC dimension, what is Vapnik? Hope I get the spelling correct. Vapnik and Chervonkis by VC dimension is the VC dimension of a set system is the maximum D such that it's the maximum D such that pi s m pi s d is equal to 2 power d. It is this maximum size of a set among take sets of larger and larger size. It's the set of size of the largest size, so that when you shatter it, you get the entire, you get all possible subsets of it. Okay. So I want to claim for the hyperplane setup. So what I want to go is for this example, I want to claim for this example, the VC dimension. Right? VC of this dimension is 2, and the VC of this is 3. So let's go over this definition a bit carefully again. VC dimension is, what is it? VC dimension depends on a set system. So it depends on a set system. And what's a set system? A set system shatters a particular set. If you take a set and when you intersect it with a set system, you get all possible subsets of that set. That's when you call it shatter. Now you ask, VC dimension is the largest set of size which is shattered by this set system. VC dimension is the largest set size which is shattered by this set system. If there is no largest, VC dimension is defined to be infinite. If the maximum does not exist, it keeps growing larger and larger and larger. It's called this one. And what we will see is several set systems when you study in this one, when you study, actually have small VC dimension that is nicely behaved, convex sets. These all have small, the actual set system can be infinite and this one, but their VC dimension is small. And once the VC dimension is small for several of these problems, you realize that several algorithms actually become much easier. VC dimension is a geometric thing that captures, it's something about the geometry of the set systems. It's how well the set system shatters this one. It says the maximum set it can shatter is of size at most d. Anything above d plus 1, it cannot shatter it into all possible 2 power d. And it say take any d prime larger than d, there will be a subset b of that set which is not obtained by intersection. Okay, so VC dimension is a definition of VC dimension clear. Any questions on the definition of VC dimension?
For the hyperplane thing, it's I mean, assuming they are not collinear, right? We're excluding the case of
what?
So 3. I mean, the VC dimension is 3 because we're excluding the collinear.
It's the maximum of, if there exists a set of size d that is shattered, then VC dimension is at least d.
Okay, got it.
Yeah, it's a max. If ever there's a set of that size that is shattered, then VC dimension is at least that size. If there's no set of that size that is shattered, VC dimension is strictly smaller than that. Okay. VC dimension, I'm not saying that every set of that size is shattered. It's the largest set there exists a set of that size that is shattered. That's all. And no larger set size is shattered.
Yeah.
Okay. Why do I care about VC dimension? So many a time in many problems, this will be an important, this quantity. We want to know how many sets, give me a particular set and give me a set X, and I want to know what is S of X. How many sets is it broken up into? This is something which we would want to study. Note that this number can be exponentially large, 2 power m. If the size of the set was m, this number could be as large as 2 power m. These are the number of ways in which X can be broken up into by this set system. If the VC dimension is infinite, in fact, they do exist sets of size for larger and larger m, pi to m can be equal to 2 power m. What we will show is, no, this can't, if the VC dimension is bounded as d, pi to m cannot grow exponentially large. This is what I'm going to prove. What we will show is so this VC dimension is a very important. This one. what we will show, set systems with bounded VC dimension bounded dimensions have height pi s m growing polynomially and not exponentially. Shoot. Okay, 1 second. You might have to. My thing just zonked out. Give me. Just give me. Just pause the whole thing. Do you see my screen?
Yeah.
Yeah, so I'm using a different iPad. My iPad has conked out. So we will prove. So what we want to say is, given the set systems, looking at set systems, yes, say with bounded VC dimension. So the VC dimension is just D. Then I want to look at how does pi s of m behave. for m much larger than d. Pi s of m can go as large as 2 power m. I want to say if something is not so large, it's actually going to be fairly bounded. So in particular, what we will show is, this is what we'll show, the sour shell. This is what's called the sour shell lemma. If you give me a set system with VC dimension D, then for all m, pi Sm is less than or equal to m less than or equal to d. So this doesn't grow exponentially. It grows only m to the d. After that, the number of, so if I know the largest set that can be shattered is of size d, now take any much larger set of size m. It cannot have like 2 power m by 2. I know that it can't be shattered into 2 power m, but I'm saying it's not only can't be shattered into 2 power m, the number of sets it can be shattered is only like m power d, not all the way like 2 power m. So just knowing the largest set that can be shattered puts a bound on much larger sets into how many things that they can be broken up into. And I want to, so this is, stare at this. We will prove this next time. I wanted to prove it this time, but I'm already past this one. But let's stare at this. The Harsha lemma is putting a strong constraint. I'm just telling you that sets of size 3. So for example, let's look at the hyperplane thing. The hyperplane set system has, so let's look at a particular example. Let's look at when U is R2 and S is the set of half planes. We know the VC dimension of the system is 3. Now I say take any set of m points and I ask how many ways it can be broken up to. So for this particular thing, this says this is less than or equal to m choose 0 plus m choose 1 plus m choose 2. That is m choose 0 is 1 plus m choose 1 plus m choose 2 plus m choose 3. So something of the order, this is order of m cubed. That's the only number of ways. If you take a hyperplane, that's the only number of ways which you can break it. You cannot break it more than that. You cannot go it all the way up to 2 power m. This is a very strong statement stating that this set system can only pick order m cube subsets of this, unlike the 2 power m. This one. It's a very geometric thing about. Once you know the VC dimension of this set system, it puts a bound on not just this particular set of size d. It puts a bound on all sets of size all the way up to any m. It's going to put a bound on that. VC dimension is a powerful statement, and because of this power is why it is used a lot in geometric problems. In geometric problems, the VC dimension, because of the nature of the geometry of the sets, the VC dimension is usually quite low, and that lets you show that understand certain things. We will see the power of VC dimension in the next lecture. But this, what I wanted to prove is Harsha lemma. So that is, the VC dimension is bounded, then the what is called the pi of m is polynomially bounded. It's not exponentially bounded. Where the exponent in the polynomial is actually d. We'll show this, but this will be an proof by the polynomial method. I'm past time, so I will do this in Monday's lecture. Okay. Any questions so far?
So for the boosting algorithm we covered some time back.
Yes.
There it was necessary for, I guess you had made it comment, right? That
there, yeah. So I'll come back to that in this one. So if the set classes which we have a bounded VC dimension, then we can do something over there, and VC dimension was needed in that place. And I'll see if we have time in the next lecture, I will complete that thing which I did but that was missing in the boosting lecture. But this is what if a set system has bounded VC dimension means this, and most nice set systems have bounded VC dimension. It's not like an arbitrary. You can, of course, build a. Of course, if you take S to be the set of all sets, then certainly the VC dimension is not bounded. It just keeps growing because certainly you can get every possible intersection. By the way, I also want to say this is tight. Why is this tight? Let's see that. The tightness of the lemma, let's just mention that. For example, S could be set of all. It could be the family of sets of size at most D. S could be family of subsets of size less than or equal to D. Suppose I take the universe and I put into it all sets of size at most D. Then this will actually be achieved. Pi SM will be equal to M less than or equal to D. Take any set and the number of sets number of things by which you will see how many sets will you see that it gets broken up into. You will see all possible D size subsets of it, at most D size subsets. So this is tight.
Prahladh, so if you only look at the set of half planes, so we I mean, so let's even in 3 we like even in R2, so we know that IS of M is at most M cube. Can we get a better bound?
So for half planes, actually, it's known better. You can actually, I think you can get M square if on the planes, not M cube.
And in general, for D dimensions, that's true.
So for in general for D dimensions, if you take instead of half planes, you take the
hyperplanes.
Good. So VC dimension of that corresponding space. So what you're asking is this following. You're asking if this is example 1. Example 2 is U is R to the D. Let's do this. And S is set of all half planes of set of all half planes. Let's call it still half planes. That is, take a hyperplane and everything to one side of the half plane. Now, certainly, I want to say a set of size D plus 1. There exists a set of size D plus 1 that is take the D plus 1 vertices of a simplex. You are working in RD. You can take the 3 D plus 1 vertices of simplex, and it's easy to see that it can be shattered. Take the D plus 1 vertices of a simplex, they can be shattered. So all I want to say is, if you take X to be the D plus 1 vertices of a simplex, X is shattered by yes. That implies that VC dimension of this particular S is at least D plus 1. There's Radon's theorem from convex geometry. That is, if P1, P2, P D plus 2 are D plus 2 distinct points, then there exists a subset of D plus 2 such that the convex combination of Pi, I in S, intersection the convex combination of Pi, I not in S is not empty. That is, I can split the D plus 2 points into 2 sets such that the convex combination of this set and the convex combination of this set will have a point in intersection. Notice this is what happened in the square case. That is, these 2 points and these 2 points, their convex combination, which was this line has a point intersection. And that point was the one that sort of messed up. The reason we say that 4 things cannot be this one. And Radon's theorem will tell you the same thing. If give me any D plus 2 points, I can split up into 2 parts such that these 2 parts will have. So in particular, I cannot do this splitting by a convex set, because if I split these guys, if I have a set, if the convex set splits these d plus points into this part and this part, it cannot do it because the convexity a point from here has to lie here, because these two convex sets are in this one. Radon's theorem tells you. By the way, Radon's theorem is not hard to prove. Just stare at it for a while, be able to. So, and this will tell you that the VC dimension of this set system has to be smaller than d plus 2. Hence, VC dimension of the half plane thing is actually equal to d plus 1. This is a generic statement. So hyperplanes, this is Radon's theorem actually gives you this. This is what you are asking, no?
Yeah, so in this case also, like when M grows larger than D, so
in this part, by the way, notice that this proof it didn't use hyperplanes at all. It only used the fact that the sets were convex. Nowhere in this proof did I use, if the sets were convex, this is true. So in particular, I could have chosen the set system to be set of all convex sets in the space, and this would have been true. The point is, that's a much stronger statement than hyperplanes, and for that, this is right. For hyperplanes, you have more geometry, you can make this thing much even better. So the set is saying, as long as the set systems are all convex, the VC dimension can't be more than the ambient dimension plus 1, period. So if you're working with very nice sets, a family of set systems are convex, the VC dimension is really, really small. You're working with convex sets in R3, R3, the VC dimension is just 4. It's not any more than 4. It's a very, the actual set system could be an infinite system and all, but the VC dimension is a small number. It's a small controllable number. And we'll see why this is a useful thing for such set systems. Okay, I will stop with this. I've already seen this one. I will somehow try to merge these two notes together and put it up online. Yeah, sorry for the iPad crashing on me. Okay, that's it. Any other questions? So we will see a proof of the Harsha lemma in the beginning of next lecture, and which will be proved using the polynomial method, and then we'll continue on to see some applications. Why having small VC dimension is a good thing. So by the way, so there was a problem on epsilon nets in one of your homework problems. So it will be good to actually look at, if you have not done the problem set, that problem, it will be good to look it up, because that will be an application which we will be actually investigating a little more as an application of VC dimension in the next lecture on Monday. Okay. Any questions, or we'll stop with this? Okay.